All right, hi everyone. Welcome back. Hope everyone had a good evening and enjoyed dinner last night. Today I'm gonna give my second lecture, which is gonna be a bit different. I learned a few weeks ago that I was speaking before Boris, which is a really good thing because for a brief amount of time, you might think that I'm good at giving Blackboard lectures, some of you, and then you see Boris's, who's renowned for giving clear Blackboard lectures. And I'll try to keep up the tradition of clarity that he started yesterday. And so today's going to be totally different. And I think actually we're diverging in a way that will be useful. Boris is going to be really into the guts of the ML feature learning calculations, presumably, amongst other things. And I'm going to sort of bring it back to physics, which is admittedly where a large percentage of my brain really lies. And so I want to start with those sort of a general recap and also discussion of neural networks and field theory and what field theory even is, and what the most general properties of field theories are. And then there's this question that is an interesting one, which is when are these neural network constructions quantum? Basically, I will just use well-known things from the mathematical physics literature to define that. That is one notion of what it might mean to be quantum, but there's definitely other valid ones as well. I just don't have as clear of a picture. And then I'll tell you about various different pictures, various different features that arise in these constructions with neural networks, in particular symmetries of the theory, the origin of interactions, how you might see and interpret phi-4 theory, how conformal symmetry might arise, and time permitting, something also about quantum mechanics. So again, I'll try to get through most of this, but if there's something that gets dropped, it's not a big deal. If at some point you want me to elaborate, please, by all means, ask me to do so. Okay, so if the notes are going to be online, so I had these notes from last year that I have adapted to a draft version of the notes for this meeting that Andre is making available online right now in case you want to follow along. I encourage you, maybe instead of trying to read it in real time, listen to what I'm saying, and then if there's a point you need clarification on, you know, I say something useful. Okay, so let's start with talking about neural networks and field theory. And to begin with that, I just want to ask a very basic question. It might seem too trivial. What is a field theory? Okay, so that is going to be part of the discussion that we'll have, and it'll even almost become a game at some point. But at the very least, I would say it requires at least some notion of the following. The first thing is fields. Perhaps not controversial. So fields are functions from some appropriate function space or sections of some appropriate bundle more generally. But some notion of fields is required. And the second thing that field theories tend to have are correlation functions, which are depend on n variables. Good. So I'm still in this land where I'm considering scalar field as a map from Rd to R. Okay. And so these x's are living in Rd. And so these correlation functions are phi of x1 through phi of x. Okay. And okay. So if these are some of the requirements, perhaps the answer to the question is that in some notion, a field theory is an ensemble of fields and a way to compute correlators. Some definition. If you're in Euclidean space, which this is RD, this is Euclidean space, one might say it a little differently, that a field theory is some statistical ensemble of fields where you have some fields and you have some probability density on those fields, and the probability density defines a way to use correlators. That was part of what Derek was saying yesterday in the context of lattice field theory. That's how it's done. But these are sort of minimal notions that are the story. And so,
can I ask a stupid question?
Sure.
Yeah. So what else is there other than a probability distribution over some appropriate space? fields? You're saying like in some other general case that we need more.
You might demand extra features beyond fields and correlators. Yeah, and one of the things that I'm going to talk about is some of the things that people might ask for. And then you might ask, should that be some minimal requirement of a field theory, or should that be viewed as a feature to be engineered? And so part of the context for that, and I'll say this again in a minute, is that over the years that I've been thinking about this, a lot of people say, hey, I like field theory. Hey, I like machine learning, sounds interesting, but the field theorists are coming from different communities with different expectations for what a field theory is, should include, et cetera. And so one of the conversations I want to have is, what are sort of the minimal things that a field theory should have? And what are the things that some field theories have that we care about that might not be true of all field theories? And so I think these are pretty conservative and minimal. So we'll talk about the answer to your question in just a second. Sure.
These things would just be further constraints and correlations.
Roughly, yes. Yeah. That's right. Okay. But so the minimal requirements, the fact that I have correlators, in principle gets us some notion of a partition function. Some z of j, which is equal to some expectation interval ddx, j of x, phi of x. And in case you forgot from the other day, recall that these correlation functions are obtained from the partition function by hitting it with enough d by dj's and setting j to 0. And so all of the information of the correlators is captured in this partition function. In statistics language, this is just the moment generating function, and the correlators are the moments. So the minimal definition of a field theory should have some statistical description, and this is the canonical one that we use. And the basic point here is that with this minimal definition, I didn't tell you yet how to compute this expectation value in here. And this is something I said the other day, but the normal way of doing this in QFT, maybe I should say normal field theory, is that z of j is the finite path interval. Okay. So we saw this the other day, but this is how we normally do it. And the other thing from the other day is that the neural network description is a different way of computing it, where this is the statistics agnostic version of the story. The normal way we do field theory says I have a specific meaning of what I mean by that expectation. It's computed in this way. And in the neural network description, you just have a different way of doing it. And this was, people might have done it before, but there was a paper from the mid-90s of Williams that computed correlators this way. And I'll write phi sub theta of x here to remind you that in this description of the theory, phi is a concrete functional form called an architecture. It has parameters theta in it. The parameters theta have some distribution associated with them. So there's some statistical ensemble of fields associated with the architecture and the distribution over parameters. And you can compute, you can study the partition function and correlators in this description. And maybe one thing to say is that these are dual descriptions. Sometimes you're not able to work with both descriptions, but the Gaussian process result that was discussed in multiple talks the last few days is basically the statement that when you have neural networks in this description and there's some large n limit, they become equivalent to Gaussian theories in this description. Okay. So you have both descriptions available to you, and whenever you have a duality, normally it's the case that you have a better control over one description than the other. But the GP case is precisely the case where you have good control over both descriptions, and you can compute the correlators either in this perspective or in that perspective, full stop.
Can I
Sure.
ask, so like the difference for you between the two is that, you know, like it's not a bijection between theta and phi. And that that's kind of the fundamentally
Yeah.
Is that fair?
Yeah, I think that implicitly in this, if you can convince mathematicians that this is well defined on a lattice, it's sort of always well defined. But in the continuum, this might be a nasty object, but the fluctuations, it's not a bijection, and in particular with the neural networks, you can just write this down by fiat from the very beginning, even if you don't know this description. And so here, the fluctuations in the fields and the networks are corresponding to fluctuations in parameters. Whereas here we have a more standard fluctuation in the field description. So this is, think of the architecture as a map from parameter space to function space. And in your guys' book and in Zohar's case, he gave an example where you can either partially or completely do an integral over the parameters and move from this description to this one. But part of the point is sometimes you can't do that integral. And even if you can do that integral, sometimes this description is just useful because this integral might be easier to do. Yeah. Yeah, that's my perspective.
When you say that dual,
What's that?
when you say that dual to each other, what do you really mean?
Good. I mean, two different descriptions of a putative same theory. So in the Gaussian process limit, what the Gaussian process result basically is that the neural network description, its statistics is completely equivalent to a generalized free field, in which case this density is Gaussian and the associated action is quadratic.
But you're assuming that statement that the thetas minus the number.
That is true. So that is the standard Gaussian process limit is the case where this is an infinite number of ordinary intervals.
And then there would be Jacobians as you transform them, so that's all taken care of when you make the statement.
If you're trying to pass from one description to the other,
Yes.
then you would need to track those Jacobians. And that's the sort of thing that these, if I recall, that's what's happening in Boris's book and in Zohar's calculation. They have this function space delta function, statistical physics help me, it's called the Hubbard-Stefanovic transform, something like that.
But then if you do all that, the statements, the correlators, they can be sort of translated into, is that the statement?
The statement is that there's various ways to get at the action that indeed relates being careful about this Jacobian. And if you know, this description is sort of like the intrinsic defining data of a neural network. If you know the action associated with it, and it is the action of the same field theory, then you could compute the correlators in either description. That's the statement. And that's the sense in which they're doing. There's two different descriptions of the same theory in principle. If you know both of the descriptions, you should be able to compute the same thing in two different ways. But as you know, in our field, we have these strong weak dualities where we often have a weakly coupled duality frame where we can compute lots of things that have strong coupling.
I can see how you go upwards.
Yeah.
The neural network description, this will be a many-to-one map.
That's a very good point. Yes. So there can be many pairs. The defining data here is the pair architecture, comma p of theta, and that there are many pairs that can produce the same function space description. And in a paper a couple of years ago, there was a toy example where I found that at large n, two different architectures reproduce exactly the same Gaussian process. So it can be many to one, absolutely.
Can it be also different, like one?
Not as far as I know, but I don't. My original perspective was that one should work very, very hard to compute and understand the action, and that's still a valuable thing. But a lot of the days, these days, my friends and I are just happy to work here because this defines correlators with ordinary integrals in a way that's perfectly well defined. You can study them and ask what sorts of field theory questions. So, any other questions?
Yeah, just to understand, according to what Boris said, the D5 thing is the sloping, and that's much like you can't measure that, but that's much more than whatever integral you have. But then you're against what?
What do you? I don't know what you're asking.
So can we tighten this up a bit, right? So supposing you have a lattice field theory,
Yes.
right? And it has n vertices.
Yes.
Yeah, so phi is object defined on n vertices. There are n of them.
Yes.
Yeah. And then you have your machine learning algorithm, and you have a number of thetas, right? Which does not have to be n, but it can only possibly be a bijection
Yes.
if it is n.
That is true because the number of degrees of freedom. That's right.
But even in that case, is it a bijection? Can you construct an equivalence between these two pictures where you have a chance that it might be a bijection?
Yeah. In the Gaussian process limit, I think it's actually totally okay. It's a standard infinite dimensional function space with an associated infinite number of parameters. The theory is completely defined by its correlators, and you can compute them exactly. Yeah. No. That's a good question. We're going to get to interactions a little later in the lecture, and I can tell you what I know. One thing that I can tell you that's a little unusual that friends ask me regularly is that in the finite neural network case, you have a finite dimensional function space. And the dimensionality of the function space can be large, but there's a question of if you limit yourself to a finite dimensional function space in field theory, how does it differ from the normal things we learn in our classes? And that's a very valid question. In general, I think one of the answers is that the leading cortex in the non-Gaussian action will have some non-localities that might be controllable. But that's sort of for further down the line. So the essential thing here is just that field theories have fields and they have correlators, and there might be multiple different notions of how to compute this expectation. And the way machine learning people compute it is this way. Anyone else? Generally, the way ML computes. Okay. So this comes to Boris's question, which is shouldn't, oh, I'm losing ink. To clarify a point, a priori, you don't know the action description associated with a neural network. And you could work hard to try to find it out. And in some cases, you can find it out. But even if you can't find it out, you can still try to do computations here. And so if what you care about is really studying the field theory, you can choose to study the duality frame that comes automatically. So let me come back to Boris's question, which is, shouldn't my field theory include X? And okay, I'll give two things here. I'll give a list of potential X's. And I'll also give a list of potential QFT, maybe I won't draw the closed bracket yet, QFT types / communities. And I'll say what X is. X is just some sort of feature. And I'm imagining some world where I'm considering some minimal notion of field theory plus features. And there's a question of what properties are intrinsic to all field theories versus what things are things that are special to some field theories that are therefore features to be engineered. And okay, so there's a whole community of people that do perturbative Lagrangians. There's a whole community of people doing lattice, both in condensed matter and in high energy physics. There's people that do something called geometric engineering. There's people that do something called the conformal bootstrap. Okay. There's people that do statistical field theory in Euclidean space that may or may not be quantum, statistical field theory. There's people that do something called constructive quantum field theory, which Demetrios alluded to in his lecture, constructive QFT. There's something called algebraic QFT. These last two are places where mathematicians love to live and prove theorems and so forth. And there's a whole list down from there. And the reason why I mentioned this is that if we're having a conversation about what is essential to field theory and what is not, we should remember that there's a diversity of different communities that define and understand their theories in a variety of different ways. And so there's a complex question about the interrelationship between these different types of field theories. And so some of the features that they might want are that you might want to have a theory that is in some sense quantum. You might want a theory that is in some sense Lagrangian. That's actually pretty clear what we mean. What we normally mean is a local Lagrangian.
Do you mean like quantization operators, or do you actually mean complex probabilities?
That's part of the discussion of what quantum means in this context. The standard thing that we would mean by quantum in a field theory is that if we're working in Euclidean, that there's a Lorentzian continuation that has proper unitary time evolution, a nice Hilbert space, et cetera. And that's where these people live, the constructive field theory people, and I'll come to that. Symmetries, some notion of locality, et cetera. And you can feel, I mean, you're here, you can add to the list if you want. And the thing when I have this discussion with people is that if we're talking about the different types of properties that a field theory might have, outside of correlators and fields, it's hard to find a property that every community will demand. So for example, particular symmetries. I love Lorentz invariants, but lots of people in this room are not studying Lorentz invariant quantum field theories, and no one thinks that only Lorentz invariant quantum field theories exist. There are statistical field theories that have no good notion of quantum as far as we can tell, and nevertheless, they're interesting to study in their own right, and they still have fields and correlators. There are theories that lots of string theorists study that are not Lagrangian. Maybe to move beyond my own immediate community, the conformal bootstrap community, people that study CFTs study spectra of local operators, and they study OPE coefficients, and that defining data is very different from a Lagrangian, even if you might have a way to get that CFT via flowing from some Lagrangian theory. So this is why I like this way of thinking about it, because all of these things are good, but it seems to me that all of these are specific features to be engineered in field theories rather than the generic part of the story. The generic part of the story involves fields and correlators. So I'm trying to think if there's something else I wanted to say there. Good. And so given this setup for thinking about it, and maybe this partially answers Boris's question, do we really want to demand something else? If we're not going to demand these things for all field theories, then there's something that could be viewed as features to be engineered. Right? So the question, if you care about, we still care about X, even if it's not totally general, can I engineer my defining data to get not just the minimal notions of field theory, but also some set of features X that might be on this list. Okay, and so whether you're talking about a CFT description or a Lagrangian description or a path integral or a neural network case, there's a question of how we actually define theories that have certain properties. Any questions? That's just like very broad brushstrokes, but the essential point is that the neural network description gets me the fields and correlators, but it doesn't necessarily get me any of these other X's. And then the question is, how might you get them? Can you get them? Yes.
The thing I was quite confusing is that it's like starting point yesterday, the Gaussian process is the 2-point function on the kernel in this 2-point coordinate.
Yeah.
It's extremely non-local. I mean, it connects everything to everything.
Yes, in general.
And so then to talk about analytic continuation and so on, that presumes there is some derivatives or something that that we can think about as time or even Euclidean time.
Analytic continuation, your idea that you introduced, is a feature that is not.
I know, but it's just hard to see any of this starting from the Gaussian processes.
Well, the question is, how would you do it? What is the framework for thinking about that? So Garrett is raising the point, this analytic continuation is the business from moving from Euclidean fields to Minkowski fields, and which is where we define Lorentzian quantum field theory with unitary evolution in real time, not Euclidean time, et cetera, et cetera. And not all field theories can do that. So absolutely, it's not clear in general that that can be done in any statistical field theory, let alone in neural network.
Well, even in say transfer matrix and Euclidean theory, there is a kind of time direction. And from yesterday, there's no time direction.
We'll come to it in a second, the constructive stuff, but in the constructive story, there is no distinguished Euclidean time direction, period, full stop, because of the full SO symmetry.
Let me just ask you, so the kind of thing you have in mind is like, could you change the architecture?
Yeah.
Could you change, something potentially dramatic, even if it's not literally what people do?
Yeah.
Day to day and construct these objects, like maybe, a locally connected neural network, could you recover
Exactly.
some kind of locality or whatever?
I.e. play with the architecture and the probability density in order to get features that you care about. Yeah, and you shouldn't expect those features for completely generic phi and p, because those features are not completely generic in field theory, period, let alone in this particular description of field theory. So that's what I mean when I say it's an engineering problem. Choose this data so that you get some subset of those, which is what this lecture is about. Make sense?
Are we not going to play, like another thing that you can do is you can play with the data distribution and then get an effective properties because of the properties of real data.
Yeah,
that's not, we're not playing with that today.
I'm not playing with that today. I have this perspective that, what is happening when you learn, if you learn with fixed architecture, what is happening is a flow in the space of probability densities on parameters. As a function of time, that thing is flowing, correlators are changing, and that, of course, is data dependent. I'm saying that at any given time slice, which any given time slice is going to give you, any given learning time slice is going to give you some P of theta, and it's going to have some architecture associated with it. And the question is, when does this data engineer these other things that we care about? And whether you care about them from a learning perspective is another question. But from a physics perspective, we certainly care about these things. So if you're trying to use this as a way to do physics, you need to address this question.
It seems like then you have to ask the second question, which is what is a neural network? You know, like if you want to play with a neural network to get a field theory of some kind.
Yeah.
Then you might ask what's allowable, so to speak.
As an architecture, you mean?
Yeah, like what classes of parameterized functions can count as a neural network, right?
Yeah, so for me here, I guess I'm considering very general classes of parameterized, some architecture composing simpler maps.
Okay.
Yeah, that's basically what I'm considering to be learning. So the thing, maybe I should answer this. Gaussian, right? So we love Gaussian theories. That's another thing, but not all field theories are Gaussian, to your point. And what's kind of remarkable about the ML literature from the 90s and subsequently, and then leading into Boris's book and so forth, is that there are many theories that are Gaussian, not many neural network theories that are Gaussian. And so if you wanted to have, you don't need a different mechanism to study Gaussian theories in physics because they have a simple path interval and you can just do it. But if you wanted a different description of those Gaussian theories, you could use this neural network description. So, so I love all of those principles, but I'm not willing to demand that any of them are absolutely sine qua non of field theory, because they're all things in particular. Oh yes, the better pen. Ooh, there's a whole stash of pens here. Forrest, get excited.
I was excited this morning already, but
Very good. All right, good. I'm gonna do this thing. Okay. So let's move on to part 2 here, which is when is one of these field theories quantum? Neural network description or otherwise, when is it quantum? Yeah, I'm not going to try to derive any new notions of what a quantum field theory is. I'm going to rely on existing things in the literature and then cast it into this language. But what do we get? If you have, there's a question which is, given a Euclidean field theory, and correlators, when is that a Wick rotation of the QFT? Okay. And part of the reason that I asked this, given a Euclidean field theory, these neural networks are generally defined on RT, so it's a Euclidean theory. The correlators are coming from this parameter space description. So this is a you can ask this generally, but you can also ask this in the context of this neural network description. And this answer, under some definition of, a Wick rotation is how we move from Euclidean space to Lorentzian space. This is something that's done in field theory all the time. But and if I'm given a quantum field theory, I can always sort of talk about studying Euclidean continuation by a Wick rotation. But if I'm given a Euclidean field theory, there's this question that isn't, well, the answer is no, I'll get to it in a second. Can I go back? And the answer is that sometimes you can go back, but not always. And so the answer to this is the subject of something called constructive field theory.
Field T, are you assuming Lorentzian locality?
I am, I'll say what I'm assuming in exactly a second. And so I'll tell what the axioms are in a second, Dimitri. But I'm going to use something from the literature, from the mathematical physics literature in the 60s and 70s called constructive field theory. The nice thing is that they are addressing the objects that the neural networks sort of give us automatically, which is the Euclidean correlators. And the answer is basically that, the answer of constructive field theory is basically that if the GNs satisfy the so-called Osterwalder-Schrader, I should write that out once at least, give these folks some credit. I guess Osterwalder begins with OS also. Osterwalder. Schrader axioms, then we can continue to a Lorentzian QFT satisfying Whiteman. And so this is clearly too strong for the general case because the Whiteman axioms require Lorentz invariance amongst other things. We'll talk about what the Osterwalder-Schradums actually are in a second, but this is the answer to this question. This is like the central theorem in constructive field theory, that there are necessary and sufficient conditions known on Euclidean correlators such that you can continue back to Lorentzian space and have a nice proper quantum field theory satisfying the Whiteman axioms. So in axiomatic field theory, the Whiteman axioms are like one of the lists of canonical axioms that people care about. Standard local Lagrangian theories in Lorentzian space all satisfy the Whiteman axioms. Okay, so this is a nice theorem, and it happens to use the data that is coming automatically from the neural network description, or really from the Lagrangian description also, because of course you can compute the Euclidean correlators in the description. So let me tell you what these axioms are.
They are necessary.
They're necessary and sufficient, yes. All of this is with the caveat that is my understanding as someone who has read some of the literature, is not a constructive field theorist there. This is the golden thread of axioms that people point to. So this is Osterwalder and Schrader. They were doing this sort of work along the same lines of what people were doing at the same time from a functional interval point of view, Klim and Jaffe, and there's this textbook along those lines. So let me draw a line like Boris and tell you what these OS axioms are.
Yeah, but very good. Just a question the other way around. So your claim was that it's always possible to remove quantum theory to get a Euclidean QFT. Yeah. Clearly you can Wick rotate, that's something.
Yes, yeah.
But I guess you're not making the assumption that the resulting theory has sense of positive definite weights or something. Because you could imagine something with a horrible sign problem. You know, are you saying that's not considered a field theory? Like take fermions at finite density without any particular symmetry?
My understanding of the statement is that Whiteman can always be continued to Euclidean, no problem whatsoever. Whiteman, for instance, is assuming Lorentz invariance. So it is definitely a narrowing of the story.
Right. So yeah, Whiteman works, but then.
That's right. So I should weaken that statement that there was this classic question that high energy physicists were asking at the time.
Right.
Before Wilson did his work, and we all thought about you guys thought about condensed matter physics, and I enjoyed, I should say. And at the time, they were asking, given Lorentz invariant high energy theory, go to Euclidean. But if I just start with the Euclidean theory, when can I come back? This is the answer.
You guys assume that X is always position.
Good. Here, there's a question of when you should consider X to be positions. Normally, in physics, the way that we differentiate between position and momentum space is some combination of notions of translation invariance and locality. And so if into your correlators, you bake some notions of translation invariance and locality, then indeed it is position, and indeed these axioms are talking about the position space correlators. So and to exactly that point, the first, well, I'm not going to write all of them super rigorously, but one of the crucial axioms is Euclidean invariance. So all of the correlators are invariant under rotations and translations. Another is permutation invariance. In the X's and the correlators. Three, I won't say too much about cluster decomposition here, but I'll tell you what it is roughly. They call it the cluster property. But what I mean, regardless of what I call it, is that if I have my correlators and I take the points in them, any subset of the points infinitely far away apart from the others, it factorizes into a product of lower point correlators. What that's basically saying is that as you take the points very far apart, you should recover the prediction of the free theory and the interaction should shut down. So that's some very weak notion of locality. And the final one is called reflection positivity. And reflection positivity is a statement that correlator, the 2n correlator, if I have x1 through xn, and I have rotations about, sorry, reflection rather, about of half of the coordinates. This just flips in some coordinate of the x1s, it flips the sign. And so there's some reflection around some hyperplane in this space that these things are greater than or. And yeah, okay, I'm not gonna prove reflection positivity or be super precise about it here, but this is a constraint on the Euclidean correlators that if you sort of derive it, where this comes from is in the Lorentzian picture. Unitary time evolution plus known states. This is the condition that is related to unitarity in the absence of negative quantum states. So this is a classic thing studied in constructive field theory. Definitely a lot of the bootstrap literature has hit onto this in various different ways the last 10 years. Just think of this as the Euclidean analog of unitarity. Yeah, there's a question.
When you say the permutation and invariance, you assume that there's only one kind of field.
In this simple case, yeah. And so there are generalizations to the multi-field case. I just don't recall.
This gives you unitarity, but it doesn't give you causality. So this doesn't apply causality.
That's right. You need the full set of axioms to get full weight. And it is known by people that work in this field in detail. If you drop subsets of the axioms, what do you lose on the Lorentzian side? But that's the one. Yes. What'd you say? Yeah, I mean, I think this is one of the Whiteman axioms. So these are the things that guarantee the Whiteman axiom. So indeed, those sorts of questions that we normally ask in field theory are captured in this set of Euclidean axioms. What? Oh yeah, I'm sorry, that's right. There is one that I left off that the GNs are tempered distributions. I had forgotten that that's related to positivity of energy, but you know, in these axioms, Osterwalder and Schrader were very careful to make sure that their axioms were sufficient to get the full set of weight. This one to me always feels like more of a technical thing, and these feel very physical. You could say something obvious. Euclidean invariance rotations under SOD and translation is the thing that becomes the Lorentz group when you continue and you rotate. It's kind of clear that some of these are needed. But this is the one, as the history goes, that was that took a non-trivial amount of time to understand. And Demetrios, in his talk, cited this paper by Jaffe from 2016 called Reflection Positivity Now and Then, or something romantic, reflecting on the importance of this condition. But maybe at the risk of belaboring the point, you can just ask, does your Euclidean theory satisfy? And if you are in the position to think about playing with architectures and densities, you can ask, how do I play with my architectures and densities to get these? And so this gives a notion of whether and another point is that local Lagrangian theories, standard variety, these scalars satisfy OS. So there's a way in, okay, so this is some condition on the correlator, there's some expectation. There's a way to write that expectation as an integral in the path integral. And there's a way for local Lagrangian theories to write this as the integral of a perfect square. And the integral of a perfect square is none.
Can I just ask about number 4? Is the quantifier that for all reflections, or there exists a reflection?
So it's for reflections about any hyperplane you choose in the Euclidean space. And the reason that is, I can just phrase it in terms of one, is because I'm also assuming full Euclidean invariance of correlators.
I see.
And so if you connect these two, it's for any reflection. And basically, it's sort of, these together is sort of the statement that if I'm in Euclidean space and all points are created equal, I can choose any direction to be my Euclidean time to continue back to Lorentzian time. And then you can sort of drop a hyperplane at tau equals 0 to talk about forward evolution and backward evolution, which is related to bras and cats and cats. So the nice thing is that none of this is my work. This is all like, this is the central theorem in constructive field theory. It is too strong of a notion of quantum field theory because it demands all of these things that condensed matter physicists, our dear friends, would not demand, I don't think. And so, but nevertheless, it is a notion of the way to do this. Okay, good.
But I think I haven't understood yet what about the data. Your P of theta really has a subscript T.
Yeah.
Which is training time, and how that evolves depends on what data you feed. So when you say you engineer something, doesn't that include engineering the data and stuff?
If you want to talk about this, so I like to think of this as I have a field theory at every time slice during training time, including at initialization.
Fine.
And so indeed, if you want these properties to persist during training, the data, the loss, and the updates have to be such that these properties on phi and p are preserved. And that's a pretty non-trivial task.
But you just worry about it at initialization.
For now, I'm talking about it just in terms of this data. And then when I talk about engineering, I would mean at initialization. But if I want it to persist during learning, I have to take into account the flow also. So that is the way to think about it in ML. If I'm thinking about it as a physicist, I'm thinking about this as just a different way to define a field theory, period. And so if this is a different way to do field theory, I don't have to talk about learning. It's just some other flow in this field theory. But so it's two different perspectives according to whether I'm talking about for ML or for neural or for field theory. Make sense? I have a P of theta at all times during learning. And I can talk about at any time slice when the pair architecture parameter density satisfies properties we care about in field theory. If you want to do it for machine learning, you have to talk about that flow as learning happens. But if you want to use this as a formalism for field theory, you don't have to care about that. Right, so that's just this very formal thing. Let's have some fun and talk about different features that we can get. And so just maybe as I'm continuing, I'll let this one be here because I've dealt with axiomatic stuff for a while. I just want to talk about symmetries, interactions, conformal symmetry, and quantum mechanics.
So yeah, I don't know if the Zoom mic is working. If it is, it just I didn't know if you were going to move on beyond this analytic continuation thing. Why is it actually relevant? Because if you were going to analytically continue to Lorentzian signature, you'd be like changing one of the coordinates of the input vectors into some Lorentzian time. Why is that a natural thing to even think about?
Yes, so I think you're asking the question in the context of for machine learning, why is that relevant? And in that context, yes. I do not have a good reason. If we learn of one someday, that's a surprise to me, frankly. I'm asking it from the point of view of if we use this formalism as a new way to define a field theory because we care about new ways of coming up with Oscar-Walder Schrader systems in field theory, that's when it matters for sure as a formalism. So Tudor, I'm viewing the formalism going both ways. It's a way to think about machine learning, but it's also a way to have machine learning data define a field theory in a new way because I have a new way to define correlators, and I can ask these classic field theory questions that the constructed people would ask in the context of this mathematics.
Yeah, awesome. Thanks.
I have an answer for why this is useful for learning, which is that if you have a theory like this, right, then you can split it up into, you can choose a coordinate at random and split up into time slices, and then you can have a perturbative theory and time slices that gives you a non-perturbative theory just as a quantum mechanical. So it can convert kind of questions of strongly coupled field theories or to questions of quantum mechanics on something that starts out.
I see.
Small. Interesting. That would be nice.
So, I guess I don't see it the full way, but maybe we can talk again a little bit after. So Dimitri thinks he sees a clear way that this enters into learning. I mean, certainly, if you wanted to have some notion of entanglement, you might need to talk seriously about quantum. But traditional machine learning, I don't see it. Sounds like an interesting idea. I think I just can't parse it.
Feel like the Euclidean invariance is true from a condition because that's transitive on RD. And phi is supposed to be equal over all RD.
This is the Euclidean invariance of the correlators.
Oh, not phi d.
No. So the Euclidean invariance is the Euclidean invariance of the field theory, which is Euclidean invariance of the correlators. So no, it's not Euclidean invariance of the fields themselves. This would be way too strong. Yes. Very
So
good.
can I ask Jim, like, why not say that this is interesting for learning if you just want to learn when you think your data might have been generated by such a theory? And just construct an architecture that's compatible with like.
Yeah.
properties of the theory, Right, I
Good.
mean,
Good. So I think you're saying if your data were the sort of data that were intrinsic to or produced by some quantum system in nature, presumably you should have your neural network assumptions respect to that inductive bias.
I mean, it seems
Yeah.
reasonable.
Yeah. No, that's a very good point.
Give me some correlators, maybe I want to predict another one,
Yeah.
or, something else about the
Yeah.
system.
So if you're doing machine learning literally with a system that is a quantum field theory, like if that's the data, then you should have neural networks that respect it. That's a very good point. Thank you. And a related point that we did dig into a little bit in the literature is that if you're in a system where you expect that your correlations have symmetries, period, you should figure out how to put it into your neural network prior and then how to have it evolve and continue respecting those symmetries as time goes on.
Yeah, that's like the equivariance stuff Maurice was telling us about, for example, it's just a different kind, like,
That-
if you look
yeah.
at QFT
That's right,
equivariance
that's
or
right.
something.
Yeah, and so we'll talk about that in a minute, ways in which it seems like these sorts of symmetries in physics are slightly different from the equivariance story. They're related, but they're slightly different. Yeah, that's a very good point. Tudor, I don't know if you heard it, but Boris was basically making the point, well, if your data is data generated by a QFT, then presumably your neural network should respect that and you should have a set up a scheme where that makes sense.
With freestyle.
Yeah, thanks for all of that.
Sure, yeah, I am freestyling. But
So
I also
what if you would take a teacher-student setup, which you have certain teacher networks that would not correspond to a field theory, certain other ones that would, because then you know the whole theta distribution.
You mean a quantum field theory? Because I think all neural networks correspond to field theories under my weak definition of has fields and has
Okay, one of
correlators.
them,
You mean one of these? I don't know. And in general, reflection positivity is a hard constraint. It's not trivial to make all of these things be satisfied. All I'm saying is that when these are satisfied, it maps onto something that is in the mathematical physics literature that is rock solid. As your community knows, reflection positivity is always under the hood and latch, right? Okay, let me continue. There's a lot more to say, and we can please keep interrupting. It's much more fun for me. Questions are great. Okay, so first let's talk about symmetries. Okay, so I have this section on features, right? And first bit is about symmetries. Okay, so in this setup, for simplicity, I'm going to be a little coy about moving back and forth between the indices. I'll sometimes have phi from RD to R capital D. Okay. Because I want to allow myself to have a vector of scalars now. For instance, if I wanted to have a symmetry in the output space. And the question that I want to ask here is symmetries of ensembles underscore neural networks. So in this story, I'm going to have phi transform to phi sub g for g in some group. And then slide. The Boris play might actually be better, but for some reason, so it's going okay, I guess. So then the statement of a symmetry, I have a symmetry if after transformation, which is what I mean by this symbol, the partition function is left invariant. So at the level of expectations, what this means is that this, recall, is equal to e to the integral ddx j of x, phi sub g of x, that's the transformed partition function. And this is just the original thing. And the basic idea is that in a neural network description, in an ordinary field theory description, this is what we mean by symmetry. This is something in particular called a global symmetry. And normally what we would do is we would transform the action. We would see that the action is invariant under the symmetry when the fields transform. If it is, we say that there's a classical symmetry. That does not guarantee that the full expectation is invariant. There's a question of whether the measure is invariant, which is the question of whether the theory has an anomaly. But if the full partition function is invariant, we say that it's a good symmetry of the full theory. And this partition function being invariant implies that all of the correlators are invariant. And so the question is, how do you do this in a neural network setup? Really a mechanism. This was something my group did a few years ago. It's pretty simple. It was probably in the literature before. First, so you're given an architecture. Remember, the data is an architecture and a parameter density, and that defines this expectation, right? So in this description, this thing is equal to integral d theta u theta e to the integral j phi. And the first step is to transform phi to phi g. Because you have a network architecture and a functional form for the field, there is regularly a way to absorb that transformation into a redefinition of the parameters. This is actually pretty similar to something Maurice was doing yesterday, but he was doing it with his kernels and his symmetries there. So absorb phi g transformation, the transformation of the field, into a parameter redefinition.
I mean, this assumes that all the orbits under G are actually represented by the neural network.
That is absolutely true, and I'll get to that in a second. Right. And then the question is the expectation invariant under, so this redefinition I'll call theta to theta g. And there's a twofold part to that question. One is the density on, okay, good. So Andre's case is that there might be some orbit as you take the symmetry group where you hit a parameter that's not actually realized. Another way of saying that is that the probability of that parameter is 0 in P of theta. It's never realized by the neural network, which is a statement that the density on parameters is not an invariant density. Yeah. So if the expectation is invariant under the symmetry, you're good to go. And it's kind of basically trivial to show. So maybe I'll just give a simple example, simpler than anything in the notes in the interest of time. So let's take phi is equal to G sub verify, I'll call it. This is any neural network. This is the parameters of that neural network. And I'm going to act on this. I'm going to act on a linear layer with this. So if I have xi, I could do a weight matrix, but a weight vector is already enough. Wi, yes. So I have an input coming into the neural network that contracts with a weight vector, and you can do a weight matrix. You can do a standard linear layer. That's not the point. And then I have literally any neural network appended to it. Okay, and the statement is that if W, good. So the symmetry that I want to talk about. Remember that this is X is in SOD is in RD. So for X in RD, I want to consider an SOD transformation. And I'll call this element R. And so phi to phi G is enacted phi G equals G. Sorry, this is a bad notation. Let me call this any neural network here. Let me call it H instead. So this is the group element, nothing to do with the neural network here appended to it. So this is now G sub phi of WI RIJ XJ, yes? Okay, and this is my transform network, but this just suggests that I should define this to be a new W prime I, okay? So I'm just absorbing the transformation of the parameter, totally trivial. And then if P of W is SOD invariant, you're done. And that's actually super trivial to realize. A standard multivariate Gaussian is enough because the multivariate Gaussian e to the minus 1/2, maybe there's some sigma squared W dot W is a rotationally invariant object. Okay. And so rotation invariance is pretty automatic in these examples. This is the mechanism. It's what we normally know from physics, just cast with one slight neural network twist. You want invariance of the partition function. You transform the field, of course. But the one extra bit is that your field is now represented by a function with parameters, and you try to absorb the group transformation into the parameters and then show that the partition function is invariant. And so when you actually do these calculations of these kernels, for instance, if you ahead of time cook it up such that it has to be invariant and you do the integral, of course, you see that it's invariant under rotations or translations or whatever it might be. Okay, so that's the symmetry mechanism. Maybe I'll give an example. A better example. So I'm going to choose cosines, but I could choose any periodic function. So I'm going to define something that I'll call Li of x, which will be some function out front that I won't worry about for a second. Cosine activation, sum on j, wij 0 xj plus bi 0. Okay, so this is some neural network with cosine activation with some multiplicative function out front. I runs from 1 to n. Okay. And so wij 0, if I draw this from I draw this such that this is rotationally invariant, and if I draw bi 0, this bias uniform between 0 and pi, from minus pi to pi, so in one period of cosine, the claim is that this theory is fully Euclidean invariant. It's invariant under rotations and translations. The rotations is exactly the mechanism I just had. I do a rotation of this. I absorb it into a redefinition of this weight matrix. By assumption, by construction, the weight matrix is, the density on that weight matrix is rotationally invariant. So the expectation is totally invariant into that. The other thing here, if I do a translation in the X, then you can view that as an effective shift in the bias. And I have set up the statistics of the bias such that when I send X to X plus C, I shift the bias to bias plus W times C. And by the uniformity, it's also invariant. And so this is fully Euclidean invariant, which is one of the Osterwalder-Schrader setups. So if you're wanting to cook those up, you need some sort of architecture that can realize Euclidean invariance. But that's one of them. So a couple of points. I can get larger Euclidean nets. What I mean by that, I'll make the point actually first here, because I already did a baby version. This property of rotation invariance persists no matter what H phi I choose after. So think of this as the symmetry of the field theory is engineered by the input layer, and anything you do after it will preserve that symmetry as long as it's the symmetry of the input. The symmetries of the input are the symmetries of spacetime. And so similarly here, if I take any neural network and act on these LIs, because the LIs have correlators that are themselves Euclidean invariant, any neural network acting on it will. So I can build deep Euclidean nets by using this as so there's something that I'll call spectrum shaping, by which I mean when you study this F function here, which is some. I meant to call it, yeah. Okay, this has to be a rotationally invariant function too, I forgot to say. This here appears in the spectrum. So this is a translation invariant theory. The 2-point function can be written as G2 of x minus y, not just x comma y. When you take the Fourier transform of that, you get something called the power spectrum. And you can use the choice of this function to shape the power spectrum. So in particular, in the case that I choose f of W0I to be this combination, don't worry about the details, I'm just writing it for pedagogy, yeah, with some parameter m, perhaps suggestively named, then if I take phi of x is 1 on root n, sum on AI, Li, I don't have to worry too much about these as long as they're IID. Here's a concrete architecture. I've specified more of the data. It's Euclidean invariant by construction, but I have chosen my f because choosing f affects the 2-point function. And in particular, in this case, the momentum space 2-point function up to normalization that I'm not going to worry about is 1 over p squared plus m squared. So this particular network construction, presumably there are others, in the large n limit gives you a Gaussian process that is exactly the normal free Euclidean scalar field. So this is the free scalar as n goes to infinity.
What was the reason that the cosine is activation function is related to what these are divided?
So I needed a periodic function there, and the reason that I do this is that when you work out the details of the translation symmetry, the details of the expectation over the b's plus the periodicity of the cosine gives you the translation invariance. Could have been a different periodic function, but I just chose it. Yeah.
F is part of the definition.
What's that? F is part of the definition of the network here. It's some overall function that depends on the weights that's out front. And I'm just pointing out that when you consider, like I could have covered that up and left it unspecified and asked about the 2-point function of this. It's going to be translation invariant. And so I could have talked about the power spectrum G2 of P of that without choosing F. And then it would depend on F. And this choice here exactly enforces this 1 over P squared plus M squared. And so that's why I call it spectrum shaping. I'd love to be able to choose networks in a systematic way to shape the spectrum of your 2-point function so that you can study theories you care about, and that's one way to do it. There's maybe many other ways, but that's something I came up with in 2021. So that's the free scalar. So like that's a nice start.
What's your mass in this case?
The mass here is just a did I trying to remember if that actually enters in the ability density. So there's one extra assumption. The mass here, think of it as a parameter associated with choosing that function f. So it's part of the choice of f. Good. I think the one thing that I forgot to say is that in this case, I choose W0 to be from the uniform distribution on a ball. Ball in d dimensions of radius lambda, where lambda plays the role of the UV path. So questions? So this is a very simple mechanism. I'll just state it one more time. Not hard at all. You're trying to show invariance of the partition function or alternatively the correlators. You transform the fields because that's what you always do. But in this case, we have a network description. And the way that we use that is we find a way to absorb the group transformation into a redefinition of the parameters such that the whole expectation is invariant. And then you're done. So you can't always do that. Not all neural network descriptions of field theory are going to be like that. But we understand how to engineer it such that you can do this. This is the neural network analog of only writing down terms in your Lagrangian that respect the symmetry.
For clarity, so if you would use this type of neural network in a loss function during training, would the loss function also be invariant, or would the training break this?
That was exactly the question that we asked in a paper a couple of years ago. you have to do some work to get the loss. You want the learning dynamic. You might imagine you want cases where the learning dynamics respects the symmetry. That depends on the data and the choice of the loss function. So you can definitely do it wrong and break the symmetry.
So can I ask actually about that? Do you care if you break the symmetry kind of in a punched or annealed way? Like, is it for every realization of the data you want the symmetry to be there? Or when I just like average over the draws of the data? Because those are two like it's much easier to set up the second one for the purposes of training. Like if your data was rotationally invariant or had some invariance properties, like its distribution.
Yeah.
From which I sampled them, you just put another average around your partition function.
And then that would be sort of automatic.
Yeah, as opposed to like for any, like it's different requirements. I don't know what you have in mind.
Right. So I think you're talking about averaging over the data distribution, and in the infinite limit, if the data distribution respects the symmetry, that extra average gets it for you.
Yeah, precisely. Like if you have it at initialization, and you have it for like the population distribution of the data.
Yeah.
You can set up at least presumably examples where you can keep it for training.
Yeah.
And otherwise it's harder because you might spontaneously break the symmetry just due to the data you observe.
That's right. That's right. And yeah, that's absolutely right. And maybe perhaps it's worth saying that sometimes we know that we want learning to break symmetry. So for example, translation invariance of a trained neural network would be very bad, because it would mean that the neural network prediction on average across initializations that you then train doesn't depend on the input, right? And so you do not want the 1-point function of the trained neural network to be 0, and that necessarily breaks translation. Or a constant rather. A constant would also be translation invariant, but that's a very bad neural. I think it was maybe in your talk also yesterday, there was this question of Art also talked about related things about which inductive biases to put in, but these questions related to symmetries, if your initialization neural network does not respect them, then it means that there's something not associated with the data a priori, unless you chose it very wisely, that's in there. So if I were to talk instead about scale invariant networks where there's scale symmetry, if my initialization neural network distribution breaks scale invariance, it means that there's some scale at the outset that has nothing to do with the learning problem. And presumably you don't want to bake that in, because in learning the actual scales of the data and the problem, you first have to learn how to ignore the one that was baked in. I think all of those questions are very relevant. And I think you're saying the data distribution and that extra average could just get it for you for free.
In some cases, for sure.
Cool. Thank you. Yeah, we should talk more about that. Okay. I talked a little bit about interactions yesterday, so I'll be brief on this. And I think I'm just, again, bit off more than I can chew. Let me talk about interactions. This is part 2 of the features. But the nice thing is that in all of this, the principles are so easy. So if you have a Gaussian neural network theory, is from a central limit theorem, then violate an assumption. And just to say a little bit more, so there's these 2 cases. One is a 1/n correction. Gaussian theories have all connected correlators, or maybe Boris will tell us later, an L/n correction. A 1/n correction, connected correlators above the second connected correlator have a vanish for Gaussian theories. That's a statement that higher cumulants vanish for Gaussians. And so 1/n corrections are the way to understand the deviations from Gaussianity. And the result of the scaling is that G2n by a standard calculation goes like 1/n to the n minus 1. And so you get the 2-point function, but all the higher, connected, it's crucially the connected one. The connected one is the one where you subtract off the products of lower point functions. Pardon? It depends on the setup. N is whatever you're taking to infinity to get a Gaussian limit. So for CNNs, it's the channels. For fully connected, it's the width. For attention, it's the number of heads, and so on and so forth. And then the other is what I'll call independence breaking. If you violate the independence assumption, what I might mean by that is, e.g., if you have Gaussian IID input weights, Um, Okay, good. Variance, yeah. Okay, so that is rotationally invariant, and it also factorizes. This is product on I e to the minus 1/2 wi, no sum up in the exponent, it's replaced by the product. Yeah. And so those are independent random variables, right? So this is one of the things you might do to get the central limit theorem to hold. But if you do something as dumb as deforming this to e to the minus 1/2 wi over sigma squared, which is what I had before, minus lambda wi squared, still fully rotationally invariant if you care about rotational invariance. But this lambda parameter prevents the factorization and breaks the independence of those statistics with the weights. They depend on each other. And if you're in a GP limit and you instead not to do a 1/n correction, you decide to break independence, you can compute basically these connected correlators G2NC will depend on lambda in some way that as lambda goes to 0, the higher one span equals its Gaussian. So these are two parameters for controlling effective non-Gaussianities. It's very simple, by parametrically violating the assumptions of the central limit theorem. Either by going to large but finite n and doing a 1/n correction, or weakly breaking the independence of the statistics.
Can I make a comment, Jim?
Yeah, sure.
So I think on point one,
Yes.
I think it depends whether you're a mathematician or a physicist.
Yeah,
For
I'm a
that one.
physicist.
Unless you're doing one-layer networks, if you have strictly more than one hidden layer, it's actually very subtle to get that order of magnitude for the 1/n connected correlation functions. It's quite a hard calculation.
I think you've emphasized this to me before, and in particular to get that L over N, it's
No, just to get the order that the little n minus one in the exponent is very hard.
because of the correlations that what if you take each one individually, the first layer to infinity and the second layer to
Yes, if you do the sequential limit, if you
Yeah.
first take the first layer to infinity, then the second layer, then you get it. But if you want to take them all to infinity together, it's very
Okay,
subtle.
right.
Precisely, well,
Right.
we can talk about why, but like for sure it's true.
Yeah.
And for one layers, it's pretty easy just because the neurons are literally independent.
Do I remember that the literature reflects this? The GP limit of a deep network was first done layer by layer, and
Yeah.
and it's because the calculation.
That's why.
Okay.
Right.
Yeah,
But yeah, that's certainly the right scaling. And any fixed now,
right.
unless you want to do L over N,
Maybe we'll hear about that.
which we all want to do.
Yeah, right. No, that's a very good point. So my cartoon that is roughly correct of the literature is that everything's CLT when they're talking about Gaussian process. But if you have deep layers, it gets a little more confusing. And so there was this original thing that Boris is pointing out, where layer by layer they showed Gaussianity sequentially. You're saying doing it all at once still is true, but it's non-trivial.
Yeah. Can I ask you about the second one too? Actually, I've never really thought about too much the non-Gaussian weights. You still get the Gaussian process limit as long as you match the first two moments in the strict infinite width limit. But I think you're saying, or maybe you're saying something different, that the 1/n corrections will look different.
What I'm saying in the strict limit, what I'm saying is that if I do the central limit theorem, I need some sort of independence assumption on the random variables that I'm adding to have Gaussianity. And if you weakly break that, you should break Gaussianity.
You need sum inside square.
Pardon me?
You need sum implicit sum inside that.
Yes, I'm sorry, yes.
I think that would be good.
Einstein, yeah. So there's a sum there. And there's a sum here. So I'm taking two rotationally invariant objects, sum on wi, and in this one I'm squaring it. This one you can factorize nicely, but there's mixing between the terms there that will cause one weight to affect another weight. That's the point.
I see. And your claim is that's enough correlation to make it non-Gaussian.
That or things like it. Yeah, that's right.
Understood.
And in particular, this is the sort of thing that should happen during training. If you imagine a genie world where I can train an infinite network very easily, and I start with IID weights, if I'm breaking Gaussianity and I'm still at infinite width, the non-Gaussianity has to come from some violation of one of the central limit theorem assumptions, and it's not in this genie world where I'm training at infinite width. It's not 1/n because I'm at infinite. And so the correlation between parameters should induce some breaking.
One more. In your first way of doing it, introducing interactions is always correlated with making the class of functions. But that's not really the case when you just look at field theory.
Yes, and I'll get to exactly that point in a second. Yes. So this version is a version of non-Gaussian entities that come with moving to a finite function space, which is a little different. And I'll do 5-4 theory now. So for a long time, I don't have a theorem against it, but I think Andre's comment is sort of a theorem against it. I wanted to get 5-4 theory bang on with a finite neural network, which is presumably pretty hard for exactly the reasons you said. And the second that I dropped that idea, I said, well, maybe I just get it from independence breaking. And as I'll show you in a second, it's automatic. Yes.
I just want to comment on your previous statement. If you take standard scaling and take n to infinity, you are Gaussian, period. And there's no correlation. If you take mean field scaling, you weren't Gaussian to begin with. So what we find, for instance, in a lot of phases of feature learning is that weights are not correlated among different width indices, they're just correlated in their internal coordinates. But so you still get correlation, but just to make the point that in standard scaling you're always Gaussian. And when you take
even with strongly correlated parameters?
Sorry?
Even with strongly correlated parameters?
No, but I thought you were saying that at finite end or at infinite end there is feature learning, and hence this correlation is also something that emerges during training. So I would argue that in standard scaling in infinite end it doesn't, just because it's strictly a Gaussian process. And if you take mean field scaling, you never have the actual Gaussian behavior to begin with, and then
Because you don't have 2.5.
Yeah.
Right. I think I'm misunderstanding slightly the order of limits you're saying. All I'm saying is something that I think is pretty conservative, that the Gaussianity emerges from CLT. If you break the CLT assumption, if you violate a CLT assumption by taking finite n, there should be 1/n non-Gaussianities. If there's some parameter like lambda that controls the breaking of statistical independence of the weights, you also have violated an central limit theorem assumption, and presumably you get non-Gaussian. That's pretty conservative.
Your example.
Yeah. But precisely because of the mixing in the cross terms. And the sum is important for that. Thanks for pointing that out, Steve.
The expansion parameter is lambda over n.
But if you do both, I'm viewing them as doing them independently, but you can also turn on both types of breaking. And then you have to talk about how lambda and 1/n compete. All right, like the questions are much better than trying to get through everything, so this is perfect. Let me tell you about 5-4 theory very quickly. Okay. I already told you here how to get the free scalar. Yeah. And so what we normally do in field theory, this is just normal field theory, but I'll write it in a statistics agnostic way, is that Z of J free scalar field theory, that basically, I just do an operator insertion where given the partition function of this theory, I just take whatever it was, this is whatever it is of the free theory, and I just insert e to the minus lambda over 4 factorial, integral of 5 to the 4th. And indeed, mathematicians complain precisely about that deformation, so I am doing it to the level of rigor that physicists normally do it. But that operator insertion is just an integrated local operator. And that is the thing that deforms the action from the free action to the interacting. It's trivial. And the point is, in the neural network description, so here, so this is a non-Gaussianity in the theory. It's a quartic. This introduces connected correlators. But I get my free scalar from a CLT. I'm still at infinite width. I haven't changed the architecture. I've just done an operator insertion. So you should ask, how did I violate one of the assumptions of CLT? And the point is, in the neural network description, phi is a function of parameters. Okay. And so in the neural network description, I have whatever P of theta I have associated with the free theory, e to the integral j phi, I do this local operator insertion, e to the minus lambda 5x to the 4th, but this literally has an equation for the parameters. So if I replace this by the parameters theta, this is an effective deformation of P of theta of the free theory to P of theta times e to the minus lambda to the 4. And I'll call this P of theta. This is free theory, not field theory. This is the P theta of phi 4. Okay. And so this local operator insertion just does an effective deformation of the parameter density. It breaks statistical independence in general, and that explains why is it that you're getting interactions in this theory from the perspective of the neural network? So this 5-4 description is still on an infinite dimensional function space for Andre's point. This 5-4 theory has interactions. We had to break one of the assumptions of the central limit theorem to get interactions, and the interactions are from independence breaking. Okay. Cool. So the principle is very simple. The GP comes from the CLT. Your interactions break it. If you go to finite n, your interactions are in a finite dimensional field theory, and you can talk about what that means. And it's an interesting question. We compute some things, but we still don't fully understand that. It's unusual. But if you want the vanilla thing, you just do the operator insertion you always do, and you interpret it as a deformation of the density on parameters of the neural. And that violates the symmetry. So it's very simple. Here's where mathematicians would say that in this function in infinite dimensional space, phi's are actually distributions, not functions, so you don't get to do deformations by that operator. And then we say we're physicists, we put it on a lattice, everything's fine, what are you talking about? But it's the standard debate. So this construction is subject to all of the normal complaints about 5-4 in 4 dimensions that people sometimes make. Most practical physicists, such as myself, don't normally worry about that because we always have a lattice in the back of our head. But this is in the neural network description to the usual level of rigor that physicists do. This is 5-4 theory. Yeah.
So where are you getting 4 dimensions? Wouldn't this be like one?
Good. By 4 dimensions, good. I should clarify. Phi is a map on our D, and so it's D-dimensional 5-4 theory technically. And I am reminding myself that in the case D equals 4, so mathematicians have ways in axiomatic field theory to treat 5-4 theory in 2 dimensions and 3 dimensions. They are very concerned about in 4 dimensions doing this stuff in patterns. So this is this thing that I normally don't agree. Yes.
If I'd like to sample from this action.
Yes.
You will talk about that or
Yeah.
What's the variance? How much do I need to sample with this exponent? Maybe I'm concentrating on a small set of data, which would be hard to sample on.
Yeah, so you're talking about doing actual practical 5-4 calculations with this?
Yeah.
Yeah, okay, so let's just put it cleanly. If we don't have to worry about computational difficulties for a moment, if you knew how to sample from this distribution, it would give you a different way to do, for instance, the Wilson-Fisher fixed point coming from 5-4 theory. Because you have a different description of 5-4 theory, and you could ask how this competes with traditional techniques. The competes with is all a question about the details of how the sampling goes, first of all, figure out this effective parameter density. Technically, you need an IR cutoff that's, well, I won't get into that. But if you could sample from this, then you would be generating field configurations as neural networks directly from the distribution of 5-4 theory, and you could look for Wilson-Fisher.
I'm not supposed to understand that there's like some computation that goes from this particular place to 5-4, right? There's no obvious
From this?
computation. Yeah.
No, I mean, you literally take this architecture and come up with the associated partition function, and then you just do this operator insertion. So it's the same architecture as the free theory, it's just the deformation of the parameter density.
Well, you insert the so
yeah.
Okay, so there's doesn't look like neural network. That now you're like integrating.
No, it's still a neural network. It's just a neural network with a different parameter density. So the defining data of this neural network description is the architecture together with the parameter density. I take the architecture associated with the free theory at infinite width, so I'm still at infinite width. I have that partition function. I do this operator insertion and I ask what it did. Well, it didn't change the architecture, and you realize putting that together with that and redefining it as P of theta of the interacting theory, it just did some deformation of the parameter density.
So like the insertion involves computing out this function, taking its fourth power and integrating it. And that's something that you would have to like convert.
If you wanted to use it practically, you would want to do that integral and then learn how to sample from the deformed density. From the point of view of like theoretically, did I construct it? That's already such. Yes.
The reality of doing things hopefully in an easier way. One, and it looks to me like you're trading a path integral for the problem of sampling.
I would say that I'm trading the path integral sampling that Garrett would normally do and his friends in Lattice with a different sampling, a different description of the theory. And both of them are plagued by computational questions. And there's a question, does this perspective sometimes offer a different way to sample that can be to leverage in the commercial? And the answer to that's I don't know. I haven't done it. But I think it's an interesting theoretical question. Yeah.
So is it obvious that adding what you do in the model corresponds to 5-1 but you said that these are the computations conditional scalar 5-1.
Sorry, say one more time.
Yeah, is it obvious that adding the deformation 1-to-1, adding that deformation 5-1 theory to get by default theory is going to be a QFT? It's obvious that that corresponds to that.
Yeah, I guess that this corresponds to the deformation. I guess all I mean by this is that this is some deformation of the action. I'm imagining e to the minus s in the normal path integral. And if you just view what an action deformation does, you can just think of it as an operator insertion in the partition.
I'm happy with the entirely QFT statement. I'm happy with the entirely neural network statement. I'm asking if doing this deformation on the neural network side, it certainly looks like 5-4, but how do you know that that is 5-4?
I guess my point is that I have a neural network description of this theory and also the normal 5-4 theory. Sorry. I have the normal path integral description of the free theory and the neural network description that I just wrote down over there. They define two different descriptions of the partition function, and I'm just saying do the same operator insertion in either. I think because they're equivalent and you do the same operator insertion, they have to be the same theories after the deformation. Seems true to me, yeah.
There's all this stuff.
Seems obvious to me, maybe I'm missing
careful
something.
with regulators on both sides. How do you know that you can do the same thing on both? Like I are like that side. We know that you can do exactly the same thing.
I guess what I'm saying is that I'm defining the new theory to be after this operator insertion. I mean, if you'd like, you could just think of doing that operator insertion and then doing perturbation theory using the partition function over there. Or you could think of it as defining the new theory. I mean, it just seems to me that because they're equivalent before the deformation and you do the same deformation to two things that are equivalent, you should get the same thing on both sides. Maybe there's some subtlety I'm not seeing, but yes.
I think maybe a way of looking at this is I mean, you talk about this mathematicians telling us 5-4 theory doesn't exist in 4 dimensions, right?
They do tell us that.
But yeah, they tell us that. But we don't care for 2 reasons, right? One is the real world is clearly not described by the 5-4 theory, so it doesn't matter.
That's also true.
Yeah. And the other is that we can say, okay, well, we'll just have our 5-4 theory as an effective field theory anyway.
It's an effective field
Then it
theory.
doesn't matter either.
It's related to the idea of put it on the lattice.
And then coming to this question here, and this worry about the regulator.
Yeah.
I think the point is that you're not absolutely guaranteed that the correlation functions you compute are for the same physical value of the coupling constant. Because there can be a relationship between them which involves the 2 regulators. And if the 2 regulators are different,
Talking about normalization.
there could be a renormalization.
Yeah. So here's my understanding of that. In normal field theory, we don't get to talk about the value of the coupling constant until we do experiments at some threshold anyways for some cutoff, and you determine the coupling at a particular value, as you know, of the effective action. And then you do Callan-Semantic, which is saying that I demand that all of the correlators are the same as I vary the cutoff. And then you see how the couplings work, right? And one way to say it is there a cutoff in this story? And indeed, this lambda here, this ball has some dimension in the parameter space. And when you work out the details, there's an effective momentum cutoff coming along with the radius of this ball of the parameters. So there is this really, I suppressed it a little bit. This really is Z sub lambda, some description of the theory, some partition function description of the theory for some fixed cutoff. And then indeed, you would do the flow by changing the radius of that ball and integrating out momentum shells. Again, something that I haven't done, but it feels like the normal thing in field theory in the sense that you should identify some notion of cutoff somewhere and then talk about how to do renormalization. And the cutoff is exactly coming from the radius. Sure, yeah, that is a little different. That is one subtlety that's a little different. I mentioned the IR cutoff. That is one subtlety that's maybe a little different. I do have other sections of the talk that I need to talk about briefly, but I'll take one more question.
Sorry, just the triviality of 5-4 is about 5 because it's trivial, so you need a cutoff. If you go to cutoff to 0, then there's no interaction anymore.
What are you saying?
The triviality of 5-4, if you're, for D above 5, which I was improved, so you need the cutoff, right?
And the cutoff is there, it's right there.
Yeah, you just get
D equals to
You can't take cutoff to infinity, you can't take the ultraviolet cutoff to infinity. Take the ultraviolet cutoff to infinity, you get free field theory.
And what happens there? If you take this ultraviolet cutoff to infinity, what this becomes is a non-normalizable probability density. It's an improper prior. And so it's a strange neural network theory. But as long as this is finite, this is a proper probability density and you can sample from it. It's just in the interest of time, I started 10 minutes late. Should I do this finish by 10:45 thing again? 5 minutes? I don't know. I can finish in 2 minutes. Let me just make the two other points. Okay, good. So all of this, so far, this is all less than or equal to 2023, specifically July. So everything I've said now is in this paper that we wrote in July 2023. And there's two results since then. One is at least in our program, I should say, other people work on this person too. I talked almost nothing about my work last time, so I'm talking more about my work this time. So in 2024, we had a conformal field result. And this is a pretty easy result for people that know what the embedding formalism is. There's an observation due to Dirac that the group of Euclidean CFT D is SO D plus 1, comma 1, which if I just go like that and you say what's that, and I say what's that group, you don't say the Euclidean conformal group in D dimensions. You say that is the Lorentz group in D plus 2 on RD plus 1, comma 1, right? And so what the embedding formalism does what the CFT embedding formalism does is it relates fields phi of x on RD plus 1, comma 1. And there's a way to restrict it to phi of x, where x lives on the so-called Poincaré section of the projective null cone in RD plus 1, comma 1. Now, that's a mouthful, but it turns out that this whole thing is just a copy of RD. So I have a way to relate fields, to study the relationship between Lorentz symmetry here and conformal symmetry 2 dimensions lower. And what our result is a way to define, this is the thing that's for the first time, this is totally known in the CFT community, a way to define a neural network version of a construction, not just relating the kinematics of phi of x that's Lorentz invariant that pushes down to a CFT on RD. Okay, and for the experts in the room, I should say that the thing, if you're familiar with the embedding formalism, the thing that was missing in the Lorentzian theory is that no one ever tried to construct directly a Lorentz invariant field theory on the Lorentzian space. What people normally do is study the CFT on RD and then view it from the point of view of 2 dimensions higher. But we're actually going the other way. We're saying define the theory Lorentzian D plus 2 and push it down. And the thing that we can do, that those functions have to be homogeneous functions, it turns out. Normally, we don't get to require that in field theory, but you can just require a homogeneous neural network. And if you get a homogeneous neural network, you can get a new construction of conformal fields. We have checked that the correlators are conformally invariant. In a toy model, we have shown that the 4-point function is exactly computable. We have done the conformal block decomposition and matched against the OPE, at least in one example, yada, yada, yada. Okay, so it's a new construction of conformal fields. Whether it satisfies in all cases the normal axioms of CFT is another question, but at least in one example, it seems to satisfy the normal story. And finally, the thing that's coming out very soon is a quantum mechanics version, which is just instead of saying phi theta of x, I'll move to d equals 1 and call it, now this is the dimension of x. Now I'll call this x theta of t to be like normal Feynman paths. So in general, a neural network description of such objects just gives you a stochastic process. But you can ask questions about when the stochastic process satisfies minimal notions, minimal requirements for quantum mechanics. This is the analog in D=1 of asking when the Euclidean field theory can be continued to Lorentzian. That's the Osterwalder-Schrader stuff. But if you do it in D=1, it's the question of whether a stochastic process is really just Euclidean quantum mechanics. Can it be continued to Lorentzian? And then we have some notions there. We have a neural network construction and a reflection positivity construction. And maybe there's some results that we really like. One of the key things that is one of the results is that I'm being brief, and I'll take questions. I'm being brief because I want to end reasonably on time. One of the results is that if you have a neural network acting on any Markov process, this is related to what Demetrios was talking about the other day. In general, it breaks the Markov condition. Sorry, I should have said something else. A known fact that was implicit in Demetrios' talk and even said is that Markov implies reflection positive, and reflection positive is this thing that's crucial for unitarity. Neural network of Markov process is not Markov in general, but is RP. And so in the same way that I could engineer my symmetries at the input layer and then my spacetime symmetries at the input layer and then do anything I want in the neural network after and have the spacetime symmetries preserved, similarly here, the reflection positivity condition is guaranteed for any neural network acting. So that's one of the main results. And the reason that we're interested in that is we want to be able to systematically construct either field theories eventually, or here just Euclidean quantum mechanical systems that satisfy this crucial property of quantum mechanical systems that are unitary. So that was very brief. That was like the last 4 pages of notes on 2 slides, but I am over time. And so I'll stop. Thank you very much.